Okay, guys, I got a new app that I'm pretty excited about in some ways, but the biggest problem with creating these videos is creating the PowerPoint, and then you've seen what happens to my handwriting, so hopefully this will help. But basically, I have this little chalkboard, and I'm going to go back and forth between a Word document and the chalkboard. I also got another little app called Snappy App that's super cool that allows me to move an image over quickly, but I can't draw on it, so I'll have to still redraw some things. Still better than the alternative though, so I think that all we have left here in quadrilaterals is trapezoids and kites. Once we finish talking about those, I'll go ahead and create that assessment. So hopefully you should have that done today and have that up for you so you can get started. Okay, so how is a trapezoid different from a parallelogram? If you look at that image there, you can sort of see BC appears to be parallel to AD, but the other two certainly don't appear to be parallel, and indeed they're not. If they were, this would be a parallelogram. So the thing that makes it a trapezoid is that it has two parallel lines only. So we call the parallel lines bases and the other two legs. So if I want to label those, then let me see what kind of chalk I've got over here. I didn't get it ready. Maybe I won't use red. I'm getting used to this program still, so give me a second here. Nope, yellow. Okay, so if I have a trapezoid, these two are the parallel ones, so I could mark that like that. But when I mark it, that means that these are the bases. So this is base 1, base 2, and this is the legs here, the ones that are not parallel. So we've talked about isosceles triangles. Isosceles triangles are those with two same length legs. Because when you look at a trapezoid, you know it has two that are parallel. If the bases were the same length, then you would actually have a parallelogram because it would force those other two to be the same length. So the thing that makes the most sense then, if we're going to talk about an isosceles trapezoid, is the non-parallel legs are the same. So basically, if you take an isosceles triangle, so that these are the same, and you chop it off, you get an isosceles trapezoid, like that. So these two are parallel, these two are the same length, and that makes an isosceles trapezoid. Oops. Isn't that nifty? Okay, so trapezoid. Okay. Oops. Did not mean to touch that. Okay. So that's what an isosceles trapezoid is. If you look at the trapezoid there on the image, I won't be able to draw on this, right? But we can talk about it even so. So we want to find the midpoints of AD and BC. AD, BC. The midpoint is there and there. And if we draw a line through that, and then we call that M and that N, so we have this line MN, that line segment is called the mid segment. So it's midway down, mid segment. If you think about it, this has a slope of some kind, right? So if you're going over and up and then over and up to get from here to here, for it to be the midpoint, you've gone the same amount over and the same amount up. So we're sort of halving this way and we're halving this way, and then we're connecting it. So that's the mid segment. The length of AB, we want the lengths of AB and CD and MN, okay? So let me come over here. I may have to sit up a little to see this better. A is -2. One, two, three, 4, 5, 6, 7. Yeah. And B is, wait, what do we want? AB. 1, 2, 3, 4, 5, 6. Also 7. CD. So actually, to get these lengths, you know what? I'm wasting time. 1, 2, 3, 4, 5, 6, 7, 8. Since it's just a horizontal line, all we have to do is subtract here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. Okay, so if I had M in, here's M, which is at -4. So from -4 to, and to get in over here, it's here. 1, 2, 3, 4, 5, 6, 7, 8. So the total is 12. Oh, I have a handy dandy eraser, so I don't have to. So Mn equals 12. So let's consider these, because we want to think about how these are related to each other. So you have 8 and 16, and then you have 12. We already just said this is a mid-segment, so it has something to do with being in the middle. And you probably would think, well, 12 is in the middle of 8 and 16, and it maybe even feels like it ought to be, right? You might feel like that should be the middle length between these two. And it is, and it always will be, but instead of saying it's the midpoint between 8 and 16, we just say it's the average. So if I add these and divide by 2, I get this. So always if I take the two legs and I add their lengths together, and then I divide by 2, I get the length of the mid-segment. Okay, so this one was 8, this one was 12, this one was 16. So the conjecture is that the length of a mid-segment of a trapezoid is the average of the bases. Okay, what's the slope of AB? You can look at that, it's 0. The slope of CD is also 0. The slope of MN was also 0. So we're going halfway from two parallel things. So those all have slope 0. So we want to have as our conjecture the midpoint. This properties business kind of got in the box where it didn't belong. The mid-segment of a trapezoid is parallel to the bases. So it's another parallel piece. Okay, for isosceles trapezoids, we get some kind of special things. So we get a line of symmetry for one thing, because the legs on either side being the same length kind of forces this similarity from left to right. So if you go to the middle between A and B and go down to the middle between C and D, it's actually a line of symmetry. So because of that, you can say that A and B must be the same because they're on either side of a line of symmetry, and C and D must be the same. So if it's isosceles, remember on an isosceles triangle that you got the two angles being congruent. So if we were on still an isosceles triangle, let me erase some of this stuff. If we have an isosceles triangle, we know these are the same. And I told you that to get an isosceles trapezoid was like chopping off an isosceles triangle. But this line has to be parallel to this one or it wouldn't be a trapezoid. So that means that this angle and this angle are the same, and this one and this one are the same. If these two are the same, since this is a linear pair with this one, and this one's a linear pair with this one, then these must be the same, because it's the thing that adds to that guy to get 180. So these two are the same. So if it's an isosceles trapezoid, this is the only way you get this kind of control. The top two angles are the same and the bottom two angles are the same, and these two lines are the same. That's what made it isosceles to start with. Okay, so the distance from A to C and B to D. Now I should have written out what A and B were again. A was -2,7. B was 6,7. D was -6, -1. And C was 9. Wait. Okay, so first we want to find AC, that's this diagonal across here. So we use the distance formula. So -2 minus 10 squared plus 7 minus -1 squared. So that's 144. 64, 208. Okay, and then BD, (6 minus -6 squared) plus 7 minus -1 squared . Okay, so we could simplify this and clean it up, but obviously the points that we're trying to make generally when we're analyzing these figures is what things are congruent. So you can see that these are the same. And of course we have an isosceles trapezoid. So with an isosceles trapezoid, what happens is that your diagonals are the same. If you have a non-isosceles trapezoid, you can make one that's got a really small diagonal and a really long diagonal. There's a really small one, there's a really long one. But in an isosceles trapezoid, you don't. So the diagonals of an isosceles trapezoid are congruent. Okay, so now we're going to do some problems, and these will be more, like what you might have on your quiz. So the first one, find x and y. So we look at this, and I'm going to go ahead and capture that. Okay, now I have that over here so I can reference it. So the top two here, aren't you guys impressed with my apps? I'm so excited. This does not actually look isosceles, but it's labeled as such, so we have to believe it. And anytime, you only trust labels. Even if it looks isosceles, if it's not labeled as such and there are no numbers that lead you to believe it, don't believe it. But this is labeled, so this is isosceles, which means these two are equal and these two are equal. So we want to find both x and y. But if we look at x right now, we've actually got nothing, right? We don't have this angle over here. These two, we know that either these two or these two will make 180. The reason we know that is because of what I sketched for you before. There's the trapezoid. These are the same, and these two make 180. So these two make 180. Same deal. So the problem is that if I compare these two directly, I've got still x and y. I have too many variables to solve. I could make the leap that these two make 180, and that would be a place to start. These two make 180, so what is x? But the more natural thing I think to do is to first set these equal. So 8y equals 120, because those triangles are equal, and then divide by 8, and you get 15. Now, from there, you can say these two equal 180, and then solve. Or you can say, well, now I know this is 120, so 3x minus 40 plus 120 must equal 180. So that puts you back in the same game that you would have been in if you'd said these two equal 180 to start with. And that would have been, again, perfectly reasonable, but not the most common thing to do first. Okay, so we have 3x then plus 80 is 180. 3x equals 100. It's kind of odd. Alrighty. So anyway, x is 100 thirds. Okay. Okay, so now I'm going to grab this one. Okay, so this one, we don't have any angles. We're just looking at lengths. But remember the thing we discovered, which is that this one is the average of those two. So what it means to be the average is 2 of 2, like we said before, was add the 2 up and divide by 2. So x plus 4 plus x plus 12 divided by 2 is 2x minus 16. So the average of the two bases is the length of the mid-segment. My goodness. It's very early in the morning for me when I'm doing this. Okay, so 2x plus 16 over 2 is 2x minus 16. So this is x plus 8. So we would subtract an x, add 16. That was annoying. Okay, so 24 equals x. I guess I need to stay out of that bottom there. Okay, so x is 24, and we found that again by just using the average of these two. Okay, on this last one we're meant to graph a quadrilateral, so I'm going to move this where I can still see the directions. I could just, move that over there, but this is kind of, perhaps needs extra space, so I don't know that I want to use it. Okay. So we've got up to 5 and over to negative 4. Ooh. Okay, so we've got 1, 3. It's A. And we have 5, negative 1. B. Okay, so let me see if I can. And we want to find the best name for this quadrilateral. Unless my sketch is totally off, then this is a trapezoid, right? At best. So we want to check, are these parallel? If these are parallel, then it's at least a trapezoid. These are not parallel, unless my graph is just awful. These are not parallel. But we can find if they're the same length. If they're the same length, then we have an isosceles trapezoid, and that's really the best we're going to get out of something that looks like this. So even when it's rotated, what you want to do is look for parallel lines, and if you see one set of parallel lines, you have a trapezoid. So the slope from A to B, the rise is 4, and the run is 4. Oh wait, the rise is negative 4, so it looks like a slope of negative 1. From D to C, we have a run of negative 8, and a rise of positive 8. From C to D again, so over up. So also negative 1. So these are parallel. So we can mark that just in case we're going to forget, which seems unlikely, but okay. So we have those parallel, and now the question is, are these the same length? That's really, we don't have many options on a trapezoid, so it's either isosceles or not. Okay, so I want to find AD. I probably should do it down here while I have more space. I want AD and I want BC. And if these are equal, then we're isosceles. So AD, we have 1 minus 4 squared. And we have 3 minus 4 squared. For BC, we have 5 minus 4 squared. And minus 1 minus 4 squared. Okay, let's see. Making sure I plugged in everything correctly. Okay, so right here, I might go ahead and stop because what we have here is 5 squared and 1 minus 1 squared is 1. And then down here, we also have 1 and 9. So once these two are the same, the fact that these two are not the same means no indeed. These are not equal. So probably I would have gone ahead and stopped right there. So they're in fact quite different. But that means that this is not isosceles, so the very best name I can give this thing is trapezoid. Okay, now we're going to talk about kites, which is the last sort of specific type of quadrilateral we can talk about. and then we can fill out entirely that graphic organizer that you had before. Okay, so this is a kite, and what a kite is, let me move this over a bit. What a kite is something which is got a line of symmetry like this. So these are the same on both sides here, which means these are the same. And of course, these are the same. These are the same. So the question about KIE and TIE is that they're the same. If I draw in KT, then these are the same, and these are the same. So these triangles are the same as each other. These triangles are the same as each other, so congruent, congruent, but not up and down. Unless it's a diamond, it's just congruent side to side. But due to all that, these are actually all right angles. So what happens is the diagonals of a kite are perpendicular to each other. So the diagonals of a kite are perpendicular. As far as opposite angles, these two are the same due to symmetry. These two are not the same unless it's a diagonal. Okay, so for this kite, we've got A and B, and the first thing is that B is 133, because these are equal. So I can just automatically state that B is 133. Because this is a quadrilateral, everything in it has to add up to 360. So, and if you, with that little line in there, that actually makes a good argument for why anytime you draw a diagonal on a quadrilateral, you're splitting it into two triangles. Each triangle has 180 degrees. So that means that the whole thing has 360 degrees. When we talk about angles in a polygon, which is one of our last things to cover, I'll use this same kind of idea. So B is 133, which means A plus 133 plus 133 plus 35 is 360. So there's 266, 301, A plus 301 is 360. A is 59. Down here, we have one thing for free. B is 90. Because it's here. A is 3x plus 5. We can solve for C also in terms of x. So C plus B plus 2x is 180, but B is 90. So C, I'll just write that in. C plus 90 plus 2x is 180. C plus 2x is 90. C equals 90 minus 2x. Okay, so now we have everything in terms of x that we could need because we have all these things that are the same. So 2x plus 5, twice. There's 2x plus 5, there's 2x plus 5. So that gets this top angle here. And then we have a plus a. So 3x plus 5 plus 3x plus 5. That's this part here. 3x plus 5 plus 3x plus 5. Again, because those are the same, so we could have just written that to start with. Plus, sorry, I ran off my line, 2x plus 2x. So this problem takes, several different applications of these things, but that's okay. So we have 4x plus 10, 6x plus 10, 6x plus 10, 4x. All of that equals 360 because it's a quadrilateral. So 20x plus 30. 20x equals 330. So dividing by 20, we get x equals 33 halves. Okay, one more kite question. And then we'll fill out our diagram. And we'll take our quadrilateral quiz. Okay, so this one we have R is S, 75 is X. We want to use the Pythagorean theorem here. So the only one that we have two things of already is that x squared plus 72 squared is 75 squared. X squared plus so x squared equals the square root of this difference, or x equals that difference, so x squared equals the square root of this difference, which is 21. Okay, so x, that's x, oh, that's y actually. So y is 21. So then we have 21 squared plus 20 squared equals c squared. And by the way, w is y, right? So y and w both 21. Okay, so we have 441 plus 400. So C and S both 29. And X is 75. Okay, so again, that was the Pythagorean theorem, which applies to right triangles. And the happy thing about having a kite is that you have all these right triangles, so you get to use the Pythagorean theorem. Okay, now let's pull this up. Okay, so we started out, this is just a random quadrilateral. Parallelogram was here. We've already filled out this left side here. Rectangle is a parallelogram that's special. A rhombus is a parallelogram that's special. And a square is a rectangular rhombus. So it's very special. Then under quadrilateral, we still have, if we have one pair, so we have two pairs of parallel sides, and that leads to parallelogram, which then gets more special as we go down. If I have one pair of parallel sides, just one, then I have a trapezoid. And maybe I have a really special one, an isosceles trapezoid. On this side, if I have no parallel sides, the best I can hope for is a kite, and there's nothing else. It's either a kite or it doesn't have a special name. So that's the rest of the flowchart. So I will create your assessments after I record one last algebra video that I forgot to do before, and hopefully should still get that up today.